So 2.3 talks about evaluating limits. So we kind of have this idea that a limit is what's happening to the output or the y value when you get close to a certain x value. And for some functions, it's really easy. Like this picture shows a line, a straight line, and it says as you approach from the left and as you approach from the right, the function's going to approach f of a, meaning it's going to approach the y value. So there's not any holes or gaps or anything funny going on. And so that leads us to this theorem that if you have a linear function, the limit of a linear function is just that function's value at the point. So, for example, in this theorem, if I had f of x equals 3x plus 2, and I wanted to know the limit as x approaches 4 of this function 3x plus 2. Well, that's just going to be f of 4. Meaning it's going to be 3 times 4 plus 2. So you just plug it in if it's linear. That's all that says. But it's not just linear functions. If I think about, well, let me kind of come down here. Well, no, it's up here. I was going to say it holds for polynomials in general. So any sort of polynomial, the limit as x approaches that number, you just plug in that number to the function. Then there's also these other limit laws. Like the limit of a sum is the sum of the limits. The limit of a difference, so the limit of this difference is the difference of the limits. So these laws are just like any sort of algebraic type laws where it allows us to manipulate those limit symbols. You also have like constant multiple. So you can pull a constant out in front is what that law says. Oops. So as I do some examples, I'll pull back and show you some of these laws. You have the product. So the limit of a product is the product of the limit. Limit of a quotient is the quotient. Wait, the limit of a quotient is the quotient of the limits. Power rule, fraction, there's all those kind of rules. And then you have limit laws. If it's one-sided, all of those above hold, except for the fractional power, because then you could have like a square root and you can't really get close to certain sides if, you know, for even roots. And so that's what this theorem is talking about. But we're not going to have to worry too much with that. We'll just deal with it when we get there. The next theorem talks about polynomial and rational functions. And again, this just means that the limit as x approaches a of a polynomial function, you just plug that number into the function and that's going to be your answer. Rational function is when you have a ratio of two functions. And again, provided that the denominator is not 0, you just plug that number into the top and the bottom and that will be your limit. Start doing some problems. So how is the limit x of a, so these are some exercises I picked from the book. How is the limit as x approaches a of f of x calculated if f is a polynomial function? And the answer to that, in you know, as far as I'm concerned, would be just to plug a into the function f of x. That is, calculate f of a. How is the limit calculated if the polynomial, the left and the right-handed limits, how is it calculated if it's a polynomial? It'd be the same as above. Plug a into the function. Because if it's a polynomial, it's going to be, you know, some sort of curve like this. And so if you are looking at some point where x is a, whether you approach from the right or the left, it's going to be f of a. It's going to be the y value at that point. And then the last question I pulled out here was, for what values of a does the limit as x approaches a of r of x equal r of a if it's a rational function? And the answer there would be for any values a that do not make the denominator equal 0. Because we can't divide by 0, so that's a problem. And so those are just a couple of review questions. Now, let's do some work. That's not the work I wanted to do. Here we go. The limits of linear functions. Literally, guys, you just plug it in if it's linear. So on this first one, it would just be 3 times 4 minus 7. And so the answer would be 5. That's it. If it's linear. Here, I mean, for the most part with limits like this, if they look nice and you can plug the number in and everything works out fine, yay, you're done. Here, 5 times negative 9, negative 45. Here, negative 3 times 2 is negative 6. Now, the last two I have here are linear, but they're constant as well. They're really constant functions. And so the limit as x approaches a of a constant c is always equal to that constant. So the limit of a constant is the constant. So notice on number 15 here, there's nowhere to plug in 6. It's not 4 times 6. If I wanted that, I'd have an x here. So the limit as x approaches 6 of 4 is just 4. Limit as x approaches negative 5 of pi is just pi. And so that's what's going on with these two problems right here. Those are both constants, and the limit of a constant is the constant. I keep doing that. Sorry, y'all. Now, the next one I have here is a polynomial. I'm just going to be able to plug this number in. So I'm going to have 2 times 1 cubed minus 3 times 1 squared plus 4 times 1 plus 5. And most of you are going to choose to do this in your calculator, but this one's too easy. Negative 1 plus 9, so I get 8. Yeah, I like that. So some of these are really easy, guys. Just plug it in. Like on number 27, I'm going to be able to plug in 1 because it's not going to make the denominator 0. So I'm just going to have 5 times 1 squared plus 6 times 1 plus 1 on the top, and then 8 times 1 minus 4 on the bottom. And then I would just calculate 5 plus 6 plus 1 over 8 minus 4. So that adds up to 12 on top, subtracts to 4 on the bottom, and I get 3. So I'm doing my arithmetic really fast, but you can see that that's all I'm doing is some arithmetic. No problems here. On number 29, if I plug in 2 to the top and the bottom, it's going to be all okay because I'm not going to get a 0 in the bottom. So here I get 6 over the square root. Well, that's 8 plus 1. So I get the square root of 9 minus 1. So 6 over 3 minus 1. So 6 over 2, which is 3 again. So life is great whenever you are able to do this with the limit. Obviously, it's not always going to be that easy. Here, I've got dealing with one-sided limits. I want to see what happens as I approach negative 1 from the left, from the right, and as I approach negative 1 of this function. And as you can see, negative 1 is a special number. So this function is a piecewise function. And basically, if I look at it in terms of kind of like on a number line, which I find helpful, it says when x is less than negative 1, then the function I would use is x squared plus 1. So when x is less than negative 1, I would use the function x squared plus 1. But when x is greater than or equal to negative 1, then I'm going to use the function y equals the square root of x plus 1. So, if I look at the limit as x approaches negative 1 from the left, I'm going to be looking at this function, right? As I approach negative 1 from the left, I'm going to be looking at x squared plus 1. But the limit laws say that I can just plug that in since it's not going to cause any problems in terms of, or since it's a polynomial. So here, this would be negative 1 squared plus 1, which would be 1 plus 1, which is 2. So, as I approach -1 from the left, remember less is left, it equals 2. Now, as I approach -1 from the right, I'm going to have to use the other function. Because as I approach from the right, the function I'm supposed to use when x is bigger than or equal to -1 is the square root. So if I plug in -1 here, I get I get the square root of 0, which is 0. And so what that tells me about the limit as x approaches -1, it tells me that that limit does not exist, because they're not the same on the left and the right side. So that's how you would approach this type of problem when it's a piecewise function. So left is less, that's how I need to use the first one. Right is greater, so that's how I need to use that function. Now, they're not always, they're not always super straightforward. Like here, it says evaluate the limit as x approaches 2 from the right of this function. Well, as x approaches 2 from the right, I can just, plug that in and get 2 minus 2, square root of 0 is 0. But it says, why don't we consider evaluating the limit as x approaches 2 from the left? Well, it's because, the way I would word it is, it's because the domain is x minus 2 has to be greater than or equal to 0, meaning x has to be greater than or equal to 2. So the function does not exist when x is to the left of 2. So the square root of x minus 2 does not exist when x is to the left of or less than 2. Also, if you think about like graphically here, this function is going to start at 2 and do this. So as you approach 2 from the right, you're good. But if you approach 2 from the left, you can't. Like, there's nothing here. So 2 from the left, it's like, what's going to happen? You can't do that. All right. Now we're going to get to some algebra. Let me make sure I didn't skip one yet. Now we're going to get to some algebra. Here's the good stuff for limits. All right, here, if I tried to plug in 1, I'm going to have a problem. If I try to plug in 1 here, I'm going to get 0 over 0. So here's what I have to do. I have to see if there's any sort of factoring or simplification I can do to help myself out here. And a big important kind of like thing to know is something called difference of squares. That is x squared minus 1, x squared minus 4, x squared minus 3, x squared minus, I did it wrong, not minus 3, minus 9, minus 16, etc. Difference of squares, remember x is being squared here, but 1, 4, 9, 16, those are perfect squares. Always factors into the sum times the difference of what it is that you're squaring. Knowing this pattern is super duper helpful for simplifying in calculus. Because now what I can say is, hey, wait, the limit as x approaches 1 of this function, I can factor the top into x plus 1 times x minus 1 over x minus 1. Well, now this reduces to the limit as x approaches 1 of just x plus 1. And now when I plug in, I get a nice number, I get 2. What's happening here in this case is that we have a rational function, and when x equals 1 in this rational function, I can't use 1. X cannot equal 1 for this equation. It's not in the domain of that equation. But as I get really close to that value, on either side, on the left and the right, that graph approaches the number 2. So just so we can kind of see this, if I were to graph x squared minus 1 divided by x minus 1, if I were to graph this, what it looks like here, this is where x is 1, I'm already zoomed in. If I come up here, it looks like y is approaching 2 when x is equal to 1. But if I go to my table is going to tell me, hey, wait a minute. My table's messed up. Let's go make this automatic. And let's change this to a 1 and a 0, make life nice. So if I'm in kind of the standard table setup, it'll give me an error. But notice as I get really close on either side of that number 1, the function values get close to 2. So what this ability to use algebra does for me is it allows me not to have to deal with the graph and not to have to deal with the tables. Oh, I probably skipped one. Yep. All right. Now, there's some algebra tricky tricks here. You know, again, if I plug in 4 here and 4 here, I'm going to get 0 over 0. So that's no good. So I need to simplify. Well, the numerator is one of those difference of squares. It's x plus 4 and x minus 4. So now that I've got the top factored, you know, this and this are not the same. So what I'm going to do to make them the same is I'm going to do a technique called factoring out a negative. So here's a little fact. A minus B is equal to negative B minus A. So 4 minus x is equal to negative x minus 4. You can verify this fact here by doing the distributive property. That would be negative b, negative times a negative is positive. So I'm going to put it like this. Factoring out a negative 1. And by the way, that's the negative 1, right? So this becomes the limit as x approaches 4 of negative x minus 4 over x plus 4, x minus 4. And so now I get the limit as x approaches 4 of x plus 4 over negative 1. Or you could have just done negative x plus 4. That would have been fine as well. And so now when I plug in, I get 4 plus 4, but I've got to make it negative. And so negative 8 would be my result here. So that's a nice little skill to know about factoring out a negative 1. Still feel like I'm skipping stuff. Alright, this one, if I plug in a 9 on top and bottom, I get 3 minus 3 and 9 minus 9, so that's no good. So in this case, and in most cases when you're dealing with radicals, you want to rationalize. If the radical is in the top, you're going to rationalize the numerator. And to do that, you're going to multiply the top and the bottom by the conjugate, in this case of the top, because that's where the radical is. And so remember, a plus b and a minus b are called conjugates. And multiplying conjugates looks like this. If you take a plus b times a minus b, you really don't have to FOIL it. But if you were to FOIL it, you would find that the outside and the inside terms cancel. So when you multiply two conjugates, you just square the first term, square the last term, and subtract them. So that's what I'm going to do here. I'm going to take and I'm going to multiply the top by the square root of x plus 3, and then I'm going to multiply the bottom by the square root of x plus 3. Now, your best bet here is to leave that denominator alone and just see what happens in the numerator. So in the numerator, according to this little formula here, this top would be the square root of x squared minus 3 squared. And so what's going to happen is that top will be x, because the square root of x squared is x, and then 3 squared is 9. And so notice it was nice that I didn't even think about multiplying out the denominator, because I'm going to be able to reduce. So now I end up with, this becomes a 1, right? X minus 9 divided by x minus 9 gives me a 1 over the square root of x plus 3. And now I can plug in, because I would have the square root of 9 plus 3, so 3 plus 3, and I would get 1/6. How long have I been doing this? Okay, so I'm going to stop here, and I'll finish some more examples on the next video.